So welcome everyone. With very short notice of this special talk, today's speaker is Gabriele Cugno.
Yeah.
And the PhD at ETH in Switzerland, and then now research fellow at University of Michigan, and you're working with Michael Meyer, and especially we're interested in like giant planet formation, as we're here about. And I heard that you are a PI of what JWST proposal.
Yes.
Program.
Yes.
So
I will discuss it.
Yeah, very much looking forward to hearing about that. So please.
Thank you very much. Yeah, thank you everyone for showing up. I know everything was a bit last minute. My name is Gabriele Cugno. I'm a postdoc fellow at the University of Michigan, mostly working on planet formation with a variety of instruments and wavelengths. So today the talk mostly focuses on some work that we have been doing with VLT NaCo, but at the end I have a few slides showing some of the other stuff that I'm working on these days. Okay, I would like to start with this very famous plot that I don't think I have to describe. On the x-axis, we have the semi-major axis. On the y-axis, we have the planet mass. And the black dots represents the solar system planets. Now, in 1995, we started populating this plot with extrasolar planets. And year after year, we found new planetary system outside of the solar system. Now, to me, the word that better describes this plot is diversity. If you look at both axes, we are spanning a range of over 5 to 6 orders of magnitudes, both in semi-major axis and planetary mass. And of course, it's only 2 parameters, but then we have to consider planet radii, chemical compositions, temperatures, clouds. We have a huge amount of parameters that we can investigate. So really, the population of planets is extremely diverse. And in order to understand this diversity, in my opinion, we really have to understand how planets formed and what are the environmental properties that would later on bring the planetary system to be what we observe today. Okay, where does everything start? In protoplanetary disk. This is something we know quite for sure. When a planet forms in a disk, it influences the distribution of gas and dust in the disk. In these simulations, I'm showing on the left side the gas surface density, on the right-hand side, the dust surface density. And we see that the presence of the planet creates some sort of spirals, gaps, and cavities. And now if we go with our instruments and try to take images of these disks, we kind of see all these structures in a multitude of disks that we were able to image. This is, for example, some ALMA images of the dust continuum. These are scatter light images taken with sphere. And these are some gas images, gas data for other systems taken with ALMA. And again, we see rings, we see spirals, we see all these structures. And now the question is, where are the planets? Are there planets? Are these structures really caused by planets? And finally, what I'm mostly interested in is really combining these 2 aspects, the population that we see today with the formation stages and the formation environment of planets in order to connect the 2 and finally obtain a coherent story. And to do this, today I'm going to talk about the NaCo-ISPY project, which is a large survey that we conducted with the VLT NaCo instrument at Paraná. So in total, over the past, over 4 years, over the past 6 years, we used 120 nights of VLT time, and we observed a total of 253 targets, all of which are surrounded by a disk. Most of them were surrounded by a debris disk, but 50 targets were surrounded by a protoplanetary disk. We always use the L prime filter, and whenever possible, we use the AGPM coronagraph. Now, because it's a large survey, we had some freedom with how to arrange our observations, and whenever the conditions, the observing conditions were not good, we were able to just request to reobserve the target with some extra time that we have. So this caused in total the 50 protoplanetary disk targets or observations that I'm describing today were taken under very good conditions, because whenever the conditions were not good, we just would repeat the observations. So overall, on average, we have very good, for example, seeing, and most or at least half of our data sets have average seeing below 0.6 arc seconds. On the left-hand side, you see some of the properties of our targets. These are just the protoplanetary disk targets. And you see that I think the two important things to keep in mind are we focused on nearby disk. Those disks that have a large separations, because when the list was compiled, we didn't have the Gaia distances. So now we know that these are larger, farther out, but actually at the beginning we thought they were quite nearby. And the stellar mass, we know that more massive planets tend to form around more massive stars. So we always chose quite massive stars. And the last important point is that we try to avoid disks that were too edge-on and focus on disks that were mostly face-on, or at least have an inclination below 60 degrees. Again, some exceptions due to the fact that the list was compiled when many disk images were not available, and afterwards we obtained these disks images with ALMA or sphere. Okay, let's move to the results. So we detected 15 companions, mostly binary systems, including 2 new binary systems that are shown on the left-hand side, and another triple system. This is new, HD 101412. It's a binary system with a brown dwarf companion that is orbiting the binary system. So it's a circumbinary companion. And finally, PD70 was published in 2018 as part of the SPHERE paper, but NaCo-ISPY provided the L prime data point. We also detected 17 protoplanetary disks, 2 of which were imaged for the first time. One of them is the Corona Australis on the right. But yeah, in total, we imaged 17 of those, and now we are deciding what to do with all these images, if there is something that we can learn from the L prime data. With all the other data sets where we didn't have a detection, we, as it's usually done in high contrast imaging, we estimated detection limits. And here I would like to advertise some work that has been done by Markus Bonse at ETH. The paper is now submitted. And we call this new approach ApplePhi. And basically, it's a slightly more robust way to estimate contrast limits than what was proposed and commonly used by Mave et al. In 2014. So the idea is very simple. Again, we are performing t-tests with injected companions to see if we can retrieve them and assess the 5 sigma contrast limit. But there are a few improvements, especially, for example, we consider the fact that if a planet is on top of a speckle, we need a fainter planet to reach the 5 sigma confidence for detection, right? While if the planet is on top of a negative speckle, we will need a much brighter planet in order to reach the 5 sigma contrast. And this is now shown by, for example, by the error bar here. So basically, we try to include the speckle field of the image into our contrast limit estimation. Another important point, for example, is that we use single pixels instead of apertures to estimate the noise. And the reason here is that neighboring aperture will always be dependent in high contrast imaging. And this is something that we should not have in order to perform a t-test. The sample should be identically and independent and identically distributed. So this is another problem that we try to solve, separating the sample and considering individual pixels. But if you want to read more, the paper should be out soon. Another big problem is the presence of disks. Again, if you look at the region marked by the green area, the noise, whenever we want to sample the noise, is for sure not independent because we have these very extended structures. For sure, it's not identically distributed, since if we are sampling the detector or the background noise, another region we are maybe sampling the disk, in other region we are sampling these very dark self-subtracted regions, right? So for sure, there are several distributions of the noise here. And in addition, if you just look at the distribution of the pixels, we see that these are definitely not Gaussian. In this plot, the gray line represents what a Gaussian distribution would look like, while the blue data points represents the pixels in our image. And we see clearly that this is not Gaussian. So again, we cannot just use the t-test assuming Gaussian distribution when this is not the case. So what we decided to do is to just remove this region of the image whenever calculating the contrast limit, and just consider regions that are clean and outside of the disk-dominated area. An important point to remember is that we are just excluding the regions where we have disk detection in our data. The actual disk, the actual protoplanetary disk, extend farther than these regions. For example, for MWC, we know that the disk is much, much larger than the 70 or so AU that we excluded here. Okay. So then, usually from the contrast limit, we try to estimate some mass detection limits. This is what is usually done in high contrast imaging surveys. Here we undertook a different approach, and I hope I'll try to convince you in the next few minutes that we should not just take a brightness from an upper limit or from a detection limit and convert it into a mass. So in this plot, I'm showing on the y-axis mass in Jupiter masses that we would estimate for PD70b in the H, in the K, and in the L prime band. Now, if we assume two hot star models like Ames-Dusty and BT-Settle, we see that for the K band and the L prime band, the estimate of the mass agree with each other. But already in the H band, just assuming two different atmospheric models, assuming the same evolutionary model, creates this discrepancy. And we already have a mass discrepancy of a factor of almost a 2. We can have a look at what the different evolutionary model would cause to our mass estimate. And if we assume a colder model like Beck's worm, we see that all of a sudden we have much larger masses for PD70b. And then we have to assume the age of the system, right? Very young stars have very uncertain age estimate. And here the shaded area represents the error bar, the uncertainty for a 3 megayear and a 5 megayear uncertainty on the age of the system. And you see that it's really tough to say anything regarding the mass of the planet just from the brightness that we observe. And then on top of this, we have to keep in mind that we might have accretion processes that contribute to the flux that we measure, and extinction might play some sort of role in diminishing the flux that we measure compared to the intrinsic planet flux. So overall, it's really hard to draw a line between a brightness that we might be able to measure, or in this case, a contrast limit and a mass upper limit for potential planets in the system. And this is especially true in the L prime band. As you can see here on the right, for PD70b, we might have masses between 4 and 16 Jupiter masses. So basically, there's no way we can put any meaningful constraint in this case.
Is that reflective of the larger uncertainty in L prime, or the larger uncertainty in the models? Or the larger spread of models? Yeah,
no, mostly. So a good fraction of it is the uncertainties in the L prime. Yes, K band is way more precise with sphere, for example, the measurements. But if you look in general, I would say that the uncertainties related to the age, for example, are much larger than prime.
Thanks.
And yeah, and then here, okay. And then here we have the mass estimates from Jason Wang and the gravity paper, where they use the extreme astrometric precision of gravity and orbital evolution models to try to infer the mass of the planet. And we see that, for example, in the L prime, it seems to be completely different than what we measure from the orbital dynamics. So I would say that it's really hard to again draw this line between brightnesses and masses for these very young systems. For older systems, this is a bit better, especially several planets we detected, for example, are part of moving groups, so we know the age very well. So this is really the special case for young forming planets. And the solutions we proposed is to assume that these planets are just simple black bodies. Observationally speaking, PD70b and C, which are the only two protoplanets we know of, have an SED, a spectral energy distribution that is consistent with black bodies. There has been the claim from gravity of some sort of very tiny molecular absorption feature, but this is not being confirmed yet. And if we look at this plot, I would argue that the data points are really consistent with a black body. In addition, a few years ago, we looked at PD70 with VLT Symphony. VLT Symphony is the European counterpart of OSIRIS. It's a medium resolution spectrograph in a near infrared. And we tried to apply molecular mapping. So molecular mapping, we used cross-correlation, spectral cross-correlation to highlight the presence of molecules in the IFU. And in this case, for beta peak B, you can really see the clear detection of water and CO in the maps. And at the bottom, we have the cross-correlation function with the two peaks corresponding to the detection of the two molecules. And now we could do the same with PD70b, and unfortunately, we didn't detect anything. And this is another piece of evidence supporting the idea that probably spectral features, if there are really weak in forming planets, and therefore it's a fair assumption, probably, to assume they behave like black bodies and they emit like black bodies. From the black bodies, we assumed some radii, and therefore we were able to estimate temperature limits that we could then bring into our detection probability map or completeness maps. Again, we consider three different radii, two Jupiter radii, 3 and 5. And on the y-axis, instead of having the mass of the planet, as it's usually done, we have the companion temperature. The only detection we have within this temperature range is HD 101412b. The reason is that PD70b and C are within the disk, so the region where they are located could not be inspected with our detection limit procedure, just because there is no way we can estimate reliable detection limit in that region of the image. And so they were left outside of the analysis. This is the occurrence rate. I think it's not important. The numbers are not important. What's important is that overall, it seems to agree pretty well with both sphere and GPI estimates for older and more mature systems. One more thing that we looked at is how do the completeness maps change when we select subsamples of our survey of our sample. So here we're showing in gray the completeness map when we look at all our 50 targets. So the distance limit is within 500 parsecs. And now the blue line shows the same when we look at systems that are within 150 parsecs. And we see that for in most regions, these two completeness maps agree with each other, meaning that basically all the statistics, all the information is provided by the nearby targets. And the farther out targets, we have poorer angular resolution, we have poorer sensitivities, and therefore they are not really providing any information when trying to do some statistics with this surveys. One more thing that we investigated is the impact of extinction. This is often neglected because we don't have a real measurement yet of the extinction through a protoplanetary disk. So here we just assumed a 1 magnitude extinction at L prime. And you see that the whole completeness map moves upwards. And this is something that we should definitely keep in mind whenever we do any type of statistics in the future for forming planets. And I would argue that we should try to find a way to have an idea, or at least have an estimate of what the extinction in protoplanetary disk might look like. Of course, it will be always dependent, or it will be different for every source, probably every position as a function of the structures, of the gaps, spirals, whatever. But at least to have an idea if we are dealing with a few magnitudes, if we are dealing with 0.5 mag, this will be really important moving forward. It's slow.
Really?
Not sure what's going on. Oh, here we go. Here we go. Finally, on this topic, I would like to compare what we could do now with NaCo and what we will be able to do in a few years, by the end of the decade, probably, with METIS at the extremely large telescope. So this is the NaCo discovery space for TW Hydra. And now we can have a look at the ELT METIS discovery space for the same target. Of course, having a such large mirror allows us to move inwards and inspect down to maybe 1 AU or at least 2 AU. And in addition, in terms of companion temperature, we are really sensitive. We will be sensitive to companions of the order of a few hundred Kelvin.
Is this for 3 Jupiter radii as well?
This is for 2 Jupiter radii. Yeah.
Thanks.
Okay. What's next? I think that one lesson that we really learned in the past years is that detecting these planets is extremely hard and extremely difficult and rare. So we definitely need to find more protoplanets if we want to learn something about them. Last year, we observed with MAG-AO-X, an instrument that probably most of you are very familiar with, or too familiar with. We observed a protoplanetary system that was also part of the NaCo survey, and we might have detected an intriguing candidate that you can see on the left-hand side. This technique is basically, we observed, this has been done for years now, and Kevin also did it very well with MAG-AO in the past. Basically, we observed the star in 2 filters, in the H-alpha filter where we include the line, and in the nearby continuum. And because the planet only emits in the H-alpha, but planets are too cold to substantially emit in the continuum, in the optical, we can use the continuum images as a reference to remove the PSF from the H-alpha images. And after this spectral differential imaging step, in this case, we just had to perform classical ADI, and this would reveal this very nice source. I have to say that this was a fantastic night, and I think we had a scene below 0.4 for most of the
Last
night.
night of the whole run.
Yes, yes. So we were super lucky.
That's very rare.
Yeah.
Yep.
Yeah.
On the right-hand side, you can see the contrast curves, again, obtained with Applefy. And you see that the blue one is simple ADI on the H-alpha data set, on the H-alpha filter, while the red one is basically the spectral differential imaging, so the subtraction of the continuum from the H-alpha, and then on top of it, we have some sort of angular differential imaging. And we can see that, especially at small separation, the contrast is really improves a lot with the spectral differential imaging step. This is because we suppress the PSF already at the beginning, even before doing ADI. So I think this really shows that moving forward, we should keep doing this very important step of SDI and keep pushing to have dual band imaging, simultaneous imaging for H-alpha and maybe other lines as well. Another project I'm working on at the moment, and this is why I'm here in Houston this week, is JWST NIRCam GTO program that targets 5 disks, which are the ones that you see here. All these disks have either gaps and rings that we think are related to forming planets, or show huge spirals in scattered light that, again, might be driven by forming planets. And finally, we have the very famous case of PD70b that we already described or discussed a few times. So hopefully we will see something. So far, what I can say is that the limits are definitely much lower than what we can do from the ground, at least beyond roughly 2 arc seconds, I would say. While closer in, we are competitive with ground-based instruments, but it's not clear yet if we're really way much better. Yep. And finally, I would like to show a few slides on JWST Cycle 1 program that I am leading. The program aims at detecting HD 163296b, which is this forming planet that has been inferred with kinks. So what is a kink? What are you looking at here is the channel map from ALMA of the disk around HD 163. These are models. So a channel map, basically, you can imagine ALMA being an extremely high resolution IFU. And a channel map represents here all the emission from the CO gas moving at the same radial velocity. Okay. If we don't have the presence of a planet, we expect to have this, we call it butterfly-shaped emission, very smooth, right? We don't expect any inhomogeneity. While the presence of a planet, when the planet's orbit disrupts the Keplerian field of the gas, and this results in a inhomogeneity along the inner edge of the butterfly. And this is shown on the left, and we call this a kink. Now, if we move to the data of HD 163296, we see that the kink is there as predicted by our simulations. This kink has been detected on several independent data sets, has been detected on different molecules, indicating that it's a physical feature that spans different altitudes within the disk, right? The CO probes the outermost disk layers. 13CO, for example, probes the midplane, right? And the fact that we see it in multiple molecules really means that it's a physical feature of the disk. In addition, we measured vertical meridional flow, so vertical flow of material from the outer layers of the disk into the midplane at the same separation. So we really think there should be a planet in there that is modifying the velocity field of the gas. Why weren't we able to find it so far? This spectrum shows a 2 Jupiter mass planet that is forming. We assumed here a relatively coldish model, so only 800 Kelvin in effective temperature. And these are the limits that were obtained in the past with SPHERE, NIC2, Keck, and NaCo. And you see that there is no way we are able to detect the planets from the ground. But if we look at what the MIRI can do with coronagraphy, we see that in several hours, we really have an extreme sensitivity, and we should definitely be able to detect the planet. This sensitivity is shown in red assumes no star. It's just the sensitivity of the detector. So probably we are a bit contrast limited, even if we are at 2.2 arc seconds. So probably our limits are going to be a bit higher than that. But this is roughly what we expect. And of course, we simulated the system. This was pre-launch. So probably the simulation now, I should repeat the simulation, but should be even more convincing. This simulation showed that we should really be able to detect a 800 Kelvin Jupiter planet with very strong signal to noise of at least 10. And again, with the actual capabilities of JWST post-launch, probably it's even better than that.
So the kink in the CO maps tells you, does that give you the approximate position of the planet in the field of view?
Very good question. Different people would give you different answers. I would say that yes, it gives you the rough position. I'm not an ALMA expert. I have the feeling that sometimes it's a bit optimistic how well we can pinpoint the position of the planet. It gives us, for sure, it gives us the separation. But we show that if our assumption is on the thermal structure of the disk is wrong, we might be off by, I would say, 15 degrees in position angle. So still we have a rough region in the image, but still we have at least a 30 degrees uncertainties on the position angle.
But it allows you to get the orientation so you don't accidentally put the planet on the quadrant.
Exactly. Yes. 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 Okay, and finally, the next step is, even if we have only a few protoplanets that we know of, we should characterize them as well as possible. And during the past year, we observed PD70b with characterize at the VLT. Characterize is a slit spectrograph with a resolution of 100,000. And these are not the real data. This is another program. These are beta peak data. And I just used those data to start playing around with the data reduction and understanding how to remove the PSF to try to detect the bracket gamma line. Okay, so the signal from the bracket gamma you're seeing here is a fake one that I inserted in the data. But this is roughly the same. So the signal I inserted in this data is the same limit that we have on PD70b bracket gamma from Symphony observations. Okay, so we should definitely be able to detect, to reach at least the limit that we had from previous observations, and this is just 1 hour. So improving even more. You still see some structures from the stellar contribution here. Improving even more the PSF removal, and including 8 hours instead of just 1, we really hope to push down the limit and hopefully detect bracket gamma. That would be awesome because it would give us the full profile of the line, and from the profile we might try to assess what is the accretion geometry of the planet. Finally, characterize now allows you to observe basically the full K-band spectrum. It has 3 different detectors, several orders. So we have the data include most of the K-band, and we hope to be able to reproduce again the molecular mapping exercise. And this time, due to the much higher spectral resolution, we hope to be able to see if the problem was extinction, and if there is a planet with spectral features behind this dusty shell, we really hope to be able to see through the dust and detect the molecular features. So the bottom plot shows the cross-correlation function that we expect as a function of different extinction levels.
How high is resolution, NaCo?
100,000.
100,000.
Yeah, between 80 and 100,000, depending on the condition. But these conditions were the data were taken in very good conditions.
What's the wavelength range?
K-band. So from
what is the range basically? Entire full K-band.
It's not the entire full K-band. I would say that within the K-band we have within the K-band we cover maybe 75% of the K-band in chunks in 8 different chunks. Okay. Yeah, separated every time by 0.1. No, 0.0 something. Yeah, it's a very cool data set. Yeah. So stay tuned. Hopefully, we will detect and finally fully resolve an accretion line from a protoplanet. Cool. This brings me to my summary and conclusions. So with I-SPY, which was the main focus of the talk, we observed 50 protoplanetary disks with the decommissioned NaCo at the VLT. I encourage you to have a look at ApplePhi, which is a bit more robust, statistically robust method to estimate detection limits based on what we already used from the Mabe et al. Procedure. I hope that you are aware that it's really dangerous to convert magnitudes to mass limits because it involves a huge amount of assumptions, and basically, depending on the assumption, we can decide what the outcome should be. Yeah, we calculated the occurrence rate for forming planets. These are roughly in agreement with more mature systems, and in the future, ARIS at the VLT, which is being commissioned now, and METIS at the ELT will provide improved ground-based imaging capabilities. And finally, JWST is ready to surprise us. Let's see what comes out. Thank you very much.
Okay, questions here.
Is ApplePhi available online before the paper comes out, or do we have to wait for the paper to learn more about it?
Since last week, it's available. Yeah.
Great talk first. I have 2 questions. One, for this candidate that you showed, can you see it in the ADI alone at a lower significance, or does it really only come out in the SDI?
It really comes out that clearly in the SDI. In the H alpha alone, there is a speckle which is the same amplitude of every other speckle.
So there is a positive source in the position in
yes,
H alpha.
yes.
Okay.
I would not call it a positive source. I would say it's really it's part of the speckle field. There is something. I mean, it's not a negative region, at least.
Mm-hmm.
Right?
Okay.
But it's really maybe 2 sigma.
But that didn't come out in the ADI, like with the rotation, if it was a speckle.
What do you mean?
I don't think I understand what you mean.
No, sorry. I meant that, whenever you have the residuals, you have some fluctuations, right? And at the position, we have a positive fluctuation. But the significance is 2 sigma, so I would not call it a positive. It's really.
So then when you do the SDI, you subtract off, I guess there's a negative speckle in the continuum that then raises the significance, or no, that's not necessarily. Because it just weakens the speckles.
Yes.
Okay.
Yes.
My other question is, so if this was actually kind of on the same question still, if this is the best night of the run, how do you plan to follow this up? I guess HST maybe?
We have HST observations planned in May.
Oh, cool. That's great to hear.
Yeah.
Oh, yeah.
That's it.
Yeah, my other question on a totally different topic is, so on these model mass estimates, you showed the difference between the H and the K and the L band, and the L band was actually giving higher masses, which got me thinking that, well, you also mentioned extinction, which I'm very happy that you did, and I agree, not enough people appreciate the problem of extinction at these young ages. So yeah, so the L band is less susceptible to extinction. If you have AV of like 10, then it's like less than 1 in the L band. So do you think that if you start off with the assumption that the models are giving you the correct mass for a particular brightness, which is probably a very bad assumption, but if you do start out with that assumption, could you maybe use this discrepancy in mass to estimate the level of extinction?
It's a huge assumption.
Absolutely.
Yeah.
And on top of it, you have to assume that there is no accretion contribution, there is no, but if you assume everything, then maybe yes. Another option that I've been thinking about is if we have a background star going through the disk, then we know very well what's the flux of the background star, right? The SED. Assuming we know the spectral type.
Also.
Yes, and so we could compare if we be able to measure the brightness of the star precisely enough, we could try to have an estimate.
That would be really cool. I'm kind of concerned that we're still going to be missing the contribution from dust in the vicinity of the planet. But yeah, I think that's a really awesome measurement that we should make.
It could be at least an initial step, right, to start understanding. Also, I always wonder if the extinction law in protoplanetary is the same as in the ISM. We always assume it is,
Probably not.
but probably not, right? So yeah, that could be a starting point.
Very cool. Thanks.
Brittany.
Can y'all hear me?
Yeah.
Yep.
Great talk. This is more of like a basic question. When you're doing the cross correlation function stuff and trying to figure out like which molecules are present, are you using a protoplanet model with that abundance enhanced, or are you just cross correlating with like the opacity curve? And are there any challenges with doing this at really high resolution for certain molecules you're looking for?
Okay, very good question. I would say that first of all, we use petty Rajans. So basically we just use the opacity tables. We created a very standard atmosphere for the planet. We put single individual molecules. So for example, it was an H2O dominated atmosphere. And then we use this as a template, as a model for the cross correlation step. We also try to combine several molecules, trying to enhance the signal, of potential features, but this didn't help. I think that we should definitely try to come up with a protoplanetary spectral model, but this, I think, it's a large problem itself. Especially to me, it's not clear right now if we don't see the spectral features because they are extincted on one hand, or maybe, because we have accretion processes, we might have a hot layer on top of the planet surface or whatever it is. And therefore, maybe the thermal structure is more isothermal, and therefore we don't have spectral features. This could also be an option. And this would require a complete new modeling approach to try to understand what is the thermal structure of a protoplanet. Regarding the high resolution, it's an excellent question, and I don't know the answer yet. For sure, there are some difficulties, especially related maybe to potential broadening. I don't know yet.
Thanks for letting me know.
Sorry.
No, it's okay. I don't know like what's wrong with certain opacities until a theorist tells me. So it's really challenging to know if you're just, trying to model your data.
Yeah. Also, at the moment, I'm still trying to remove the PSF or remove the stellar contribution. But the KEC team showed that it's probably best to model the stellar contribution and then fit the stellar plus planet contribution instead of a stellar contribution only, to show that the model describes the data better. So this is a different approach that I would like to investigate in the future. And maybe it's even better than trying to filter out the stellar contribution. This is still to be investigated.
Gotcha. Thanks for sharing that with me.
Okay, any other question from the audience here or online? Okay, then let's thank Gabriele again for the
Thank you.
talk.